yeah, one of the massive perks of having our Zooms on, our SciBars on Zoom at the minute, is that we can attract people like James, who is from the southwest of England. So we wouldn't normally get him up in Chester. He's a software developer and a mathematical communicator, which I must admit is a job title I hadn't heard of before James got in touch. He's passionate about spreading maths to the masses, and that includes little forays onto Radio 5 to talk about political things and current affairs with a mathematical slant to them. And just because he's got nothing else to do, he's currently learning Mandarin Chinese. Just because, why not?
Why not?
So without further ado, take it away, James.
Hello. I'm going to talk to you about primes. Primes are interesting to me. I like them. They're numbers. All of numbers are interesting. So you probably already know that the name of this talk is Primes, Finding Patterns Where There Probably Maybe Are None. And I'm going to talk you through some of the more classical parts of mathematics and the less classical parts of mathematics, and we can just talk about them and look at them and enjoy maths for what it is. So to begin with, I should probably mention what is a pattern, because to some people a pattern will be the English definition of a pattern. To other people who are more mathematical, I know there are some of us here that are more mathematical, but I'm sorry, we're going to go through this now. So basically, a pattern is something that, I've not named this slide correctly, but we'll come back to this. A pattern is something that can be defined by a law. Patterns may or may not exist. So some things just don't have patterns. If you're interested, go look at chaos theory. There's a lovely bit of maths all about things that are very hard to kind of actually describe. And a pattern can be a universal law, it can be a formulae, or it can just exist. The more complex the pattern, the more mathematically bogged down the rule becomes. Say water, we've got to use things like the Navier-Stokes, which are one of the millennium problems, which we basically don't know whether they're well behaved. So finding or describing water in certain areas is very hard. Also, a couple of notes, mathematical notes, because people will complain. Unless I say otherwise, we are talking about positive integers, so numbers 1, 2, 3, and 4. No, tonight is not my proof of Goldbach's conjecture. That's next year. Join me on the 31st of February. And as Sean has already said, if you have any questions, put them in the chat, mathematical or not. Or if things I haven't explained something properly and you want to understand a bit more, please put it in the chat. I've got paper, I've got visualizer, which you'll see in a minute, and I'm more than happy to run through anything you don't understand or any proofs or anything that you just want to know more about. So, without further ado, what are the primes? This is the first section. I've split the talk up into sections. This is the first. This kind of goes through what's a prime, how many are there, is one a prime, and how can we test for a prime? If you just gave me a number, how can I know it's a prime or not? Primes. What and how? They're lonely. I think of primes as these lonely numbers sitting on the number line. We've got a lovely long number line, and there are these numbers that are lonely. The poor old primes only have two friends. They have one and themselves, but technically, if we're talking about real life, they have one friend, which is 1. And the lonely numbers, or the primes, are 2, because 2 only has two friends, 1 and 2, 3, 1 and 3, 5, 1 and 5, 7, 1 and 7, and 11, 1 and 11. They're the only two numbers that divide it, if we want a more mathematical term. So they are primes. There are more, but how many we'll come back to later. How many are there, though? If I told you that if you give me some primes, I can always find another one, would you believe me? Well, you should, because I can prove it. we can take, imagine there are only 3 primes, 2, 3, and 5. We can take these numbers and we can multiply them together. So we can take 2 times 3 times 5, which is 30. And now we can take this number, which is 30, and we're going to add 1. So we get 31. And we have a new prime number. Trust me, it's prime at the moment. We'll come back to showing this prime later. So we have 3 primes in our example, and we have proved that they're not 3 primes, there's actually 4. So then we can take these 4 primes, we can put them back into the process we've just done, and we get a 5th prime. Take those 5 primes, put them back into the process, you get a 6th prime. And you can keep on doing that until you it gets ridiculous and you say, okay, there are infinite primes. There's no bound on how many primes. They're a bit like rabbits as well. Put them in a bag, you can always pluck out one more. But there is this black sheep of the family. We have 1. Is 1 a prime? A lot of people, well, the Greeks originally thought 1 was a prime, and I think until the 1900s, people were saying that 1 is a prime. But we've kind of come to the conclusion that it's probably not. The reasoning goes along the lines of it only has 1 friend, not 2. So if 1 was a prime, then it would have 2 friends, 1 and itself. But itself is 1. So it would have only 1 friend, technically 0, because you can't be friends with yourself. So no, 1 isn't a prime. We class it differently. We call it a unit, but that doesn't concern us tonight. We just need to know that 1 isn't a prime. 1 being a prime is makes a lot of mathematical things work nicely. If 1 was a prime, we'd have to define some of the most important prime things that we'll come to later on. So this slide says 1 is not a prime. We don't have to worry about it. So, okay, I have a number. Let's take 31, because 31 or 37 or whatever number you want. And we can test for primality. To test for primality, there are 2 ways that I'm going to mention. The first is we can divide our number by every prime between 1 and the square root of that number. And if the number isn't divisible by any of those other numbers or primes between 1 and the square root of the number, it is itself prime. So let's take an example. Let's see if 37 is prime. We can take 37 and we can take the square root of it, which we know is approximately 6, because 6 squared is 36. The square root of 37 is 6.06, I believe, about. It doesn't matter. It's approximately 6. So we have to take all the primes between 1 and 6, which we know there are 3. There's 2, there's 3, and there's 5. And 37 isn't divisible by 2 because it's not even. 37 isn't divisible by 3 because it's, well, you can add up the digits and do a digit sum and you get 10. And if the digit sum of the number is divisible by 3, then it's divisible by 3. 10 isn't divisible by 3, so the number isn't divisible by 3. And it's not divisible by 5 because it doesn't end in a 0 or 5. So 37 is prime because all of the primes between 1 and the square root of 37 don't divide it. So 37 is prime. Throughout the talk, if I'm talking about some rather complex maths, I'm going to add this slide here. It kind of just indicates to you that the next bit I'm talking about something that's slightly more difficult than the rest of the talk, and it may take a bit more understanding, or if you don't like maths, don't worry about it. So factorials. Factorials are a mathematical way to do a simple operation. If we take a number, say 5, then we can calculate 5 factorial by doing the following. We can take 5 multiply it by 4, multiply it by 3, multiply it by 2, multiply it by 1. You can see the pattern there. And that's 120. So we could do something for 4 factorial. 4 factorial would be 4 times 3 times 2 times 1. And you can do that for any number. And we denote it with an exclamation mark. So we've got a 5 exclamation mark, or for computer scientists, 5 bang. And that's factorial. It's not that bad. This is where it gets a bit funny, because I can't tell the clock. Well, I can't tell the time of the clock. And these are usually known as clock arithmetic, but we're going to explain it a slightly different way. But if we have a division, say 5 divided by 3, when we all first learnt division in school, we were taught about something called remainders. So the remainder when 5 is divided by 3 is 2. You never saw remainders again. Nobody ever talked about them. I wondered where they went. They went here. Modular arithmetic is basically a remainder. So we write it as 5 mod 3, which is 2. And 5 mod 3 is basically the remainder when we divide 5 by 3. So 5 mod 3 is 2. Or to take a different case, if we have 6 mod 3, we know that 6 is divisible by 3. So 6 mod 3 is 0, because when we take the remainder of 6 divided by 3, there isn't any. This is what modular arithmetic is. So now on to something slightly more complicated. Our second test, which is called Wilson's theorem. If we take a prime, or a number, a p, and we want to know, this p is any number, and we want to know this number is prime. We want to test. So if p is prime, the remainder of the factorial of p minus 1 divided by p will be p minus 1. That's a bit complicated, so I'll say that again. A number is prime if the remainder of the factorial between remainder of p minus 1 factorial divided by p, if that remainder is p minus 1, p is prime. So let's do another example, because examples are useful and they're good. So if we let our number p be 5, and p minus 1 is 4, and 4 factorial, which is 4 times 3 times 2 times 1, that's 24. So we want to know if 24 divided by 5 is p minus 1, which is 4. So I'm going to do 24 mod 5. And we know that 24 on 5 is 20 on 5, add 4 on 5. Just some fractions. And because we're taking a remainder, we know that 20 divided by 5 is a whole number. So we can disregard that bit. So we've got 4 on 5, which means our remainder is 4. It's just a different way of talking about remainders or writing them. So if we divide 5 minus 1 factorial by 5, we get 4. And 4 is 5 minus 1, so 5 is a prime. This is just another way of telling if a number is prime. It's notated like this, but it's a bit scary. It looks scary. I thought it was scary when I first saw this. But don't worry about the notation if you're a bit mathophobic. It's fine. The notation isn't really important. All that's important is that you can see that this is a way of telling if a number is prime. So we subtract 1, divide it by the number. If that remainder of that is 1 less than our original number, then the number is prime. That's all. So we can move on to something slightly more palatable. We can talk about history. And we're going to talk about the Sieve of Eratotheres, Quadratics, Green-Tao Theorem, which sounds scary, but it's not actually that scary. The truth about prime formulae, and GIMP, which I shall unabbreviate now. It's the Great Internet Mersem Prime Search, not anything else. So let's go. So we've got a model on the left-hand side that was created by somebody I know. I met them at a maths event last year where it was November, December last year. And they showed me this model. And they said to me, okay, here's something interesting. I have a model here. I 3D printed it. And he took the pieces you can see in front of me. He took the 2, and then he put the 3 on top of the 2, and he put the 4 on top of the 2 and 3, and he put the 5 on top. And what was interesting about this model is that you could see through certain holes. Mathematically, what he'd just done is he'd created a Sieve of Eratotheres, which kind of uses a simple idea. It was from the Greek era. The earliest known reference of this sieve is from Nicomachus's Introduction to Arithmetic, where it describes this sieve and it kind of attributes it to Eratotheres of Cyrene, who was a Greek mathematician. It uses the fact that a number is one of 2 things. This number is either prime or it isn't. And I'm using a fancy word here, composite, because we know by the fundamental theorem of arithmetic that a number is either prime or it's the multiplication of primes, which again, we don't need to worry about too much, but we need to know that a number is prime or not. There's no middle ground here where the number could be prime and it could be not prime. It's either prime or not. There's no mid ground here. They're 2 completely different sets. And so we can use this fact and we can go through and we can remove multiples of 2 from a number line, and then multiples of 3, and then multiples of 4, and then multiples of 5. And eventually we're left with just the primes. If I move over to, I don't know how, no, it's this one, isn't it? Is it this one or is it this one? I'm unsure. It's doing, right. No, it's this one. This one? There we are. Hello, you should be able to see me writing stuff. So if we take 1, 2, 3, 4, 5, 6, 7, 8, 9, and put 10. What we're going to do now is we're going to do a simple number experiment. We're going to create our own Sieve of Eratotheres. So we're going to ignore 1 because 1 becomes an annoyance. So we're just going to box it. So let's take all the even numbers. What we do is we circle the first number because we know that we're starting off with a prime, so 2 is going to be prime. Then we're going to cross out all of the even numbers because they're no use to us, they're not prime. So let's look at the next number. We've got 3. Okay, we know that's prime because it's the first one here. We can get rid of the multiples of 3. We've got 3. Oh, 6 is already gone. Let's cross out 9. Okay. And now let's go for 5, which is the next number. We know that's prime because it's not crossed out yet. And okay, so are there any other multiples of 5? No. Okay, 10's already crossed out, and we have 7 left. So we've done a quick and simple Sieve of Eratotheres to just get some primes under 10. The brilliant thing about the Sieve of Eratotheres is that it's good at doing small numbers. If you have a small number of primes, then you are more likely to use the Sieve of Eratotheres than another method we'll see later on. But if you've got larger, you'll need a different way of doing it. But this was the Greek times, and this was a massive step forward from just taking a number and saying, okay, brilliant, here's a number, let's divide it by 1, divide it by 2, divide it by 3, and then go through all the primes. This was a massive step forward. This was kind of the first breakthrough in prime number theory. So let's look at another sieve. This is the Sieve of Atkin. This was a lot later. This was from 2003, which, although does sound quite a long time ago, it's 17 years now, it's a lot closer to us than the Greeks. So this was a more efficient sieve. It was found in 2003, and it was found by A.O.L. Atkin, who it's named after, and Daniel J. Bernstein. So the Sieve of Atkin was born. Using old Greek ideas with modern computation of computers, more primes could be sieved ever more effectively. Obviously, there are problems here. The Sieve of Eratotheres is infinitely better at smaller numbers. But the Sieve of Eratotheres has its problems. And when you get to a larger number, as you can see on this graph, and yes, that is a very large number, that's 10 to the 10. But still, we'll see later that primes, we're searching decently above that value. And you see that the Atkin comes into its own. The Sieve of Eratotheres goes up exponentially from there, and the Atkin follows a nice smooth curve. So it is infinitely better for larger values of the prime. So what makes this so much better than the Sieve of Eratotheres? One thing, it relied on the number 60. And you may not think 60 is special, but 60 has 3 very important factors. It's got 2, 3, and 5. These factors are prime, and it means you don't have to check off all the multiples of 3 and all the multiples of 5 and all the multiples of 2, which, although it may seem that they are kind of pretty trivial numbers, they remove a lot of computation. They remove, I think it was like half when you get to larger numbers, and it was kind of then move forward that they could use the squares. If a number is a square, then it's obviously not a prime. And if a number is a square of a prime, it's definitely not a prime. But we can move this one step forward. We can take a number like 22 or 30. 22 is not divisible by any square number. And by square number, I mean a whole square number where the square root of that number is a natural. So it's 1, 2, 3, 4, not 2. Saying 2 is a square number is not. I want square numbers where the square root is a natural number. And because they're square free, you've already, again, you've knocked off several possibilities for it not being prime. Obviously, the 2 numbers I've chosen here can't be prime because they're even. But still, if you took an odd square free number, something probably, I think 31 is square free if I remember, but 31 is prime. 31 prime? 31 is prime. But you've taken an odd number. Odd square free numbers aren't prime, are few and far between, I remember from my research. But still, if a number is square free, it's a lot more likely that it's a prime number. This Sieve of Atkin also used some number theoretical results. That I won't mention here because they're confusing and they would confuse a lot of people without looking into them in great detail, so we won't go into them here. But if you're interested, please do put in the chat, and I am more than happy to go through how this actual sieve works, because I think it's really interesting. But I don't want to scare people. I'm really scared of scaring people. So we won't go into this here, but I'm more than happy to do it at the end. So, quadratics. Yeah, I'm aware. You remember them. We all remember them. You remember quadratic formula and factorizing, and we're not talking about the here. No, it's nothing like we did at school. We're just talking about equations that are of the form ax squared plus bx plus c. But first, I want you all to pick a number. Pick a number between 1 and 40. Remember that number. We're going to do a little experiment with it. Depending on how brave you are, you've chosen either a very small number or a very large number. People choosing large numbers, good luck. Square it. Take a number and square it. I should probably mention, if you have a piece of paper, it would be very useful. Paper's good. A mathematician always needs a piece of paper. I was told that very early on in my mathematical education. Also told that, well, squared paper is good, but it restricts the flow of the mathematician, and one should only write on plain paper. I didn't hold to that, you see. I like lined. Well, I do like squared, but I don't have any squared on me at the moment. But if you've got their number and you've squared it, subtract your original number. So you've got a square number. Now you're going to subtract your original number. Mathematicians out there probably know what the next step is. I know somebody's in the audience tonight who knows a lot about primes and really likes primes. So I'm sure they've already seen this before, but it's fun. I like this. This is always a quintessential part of a prime talk. Right, now you've squared your number, subtracted your original number, add 41. And you should have done that by now, hopefully. I think, well, I'm slow at modular arithmetic, but I've kind of done that in my head. And your number is a prime. It must be. It will be a prime. If anybody's got any complaints, I shall open the chat, but everybody should have primes. Oh, yeah. Primes. Love primes. Yeah, it's a prime. If it's not a prime, your mental arithmetic's gone wrong. Because I trust Euler. Also, over here, I'm also while I'm on the slide, this is a spiral of Ulam, which is another way, well, it's another Euler thing, I think, if I remember correctly from my research, that this, all the ones in blue are primes of form 4n plus 1. I think it was quite pretty. I'm not going to talk about it tonight, but I think it's pretty. So, you've all now done your calculations and you've all made a prime. Oops, come on, behave. Right. All of your numbers were prime. That's the fact. What you did was you plugged a number into the quadratic n squared minus n plus 41. Because what this says is if you've got a number n, we can take 2, we square it, which is 4, minus n, which is 2, so that's 4 squared minus 2, which we know is 2. Sorry, 2 squared minus 2, which is 2. And then you add 41, which is 43. And 43 is a prime number. I'm not going to prove that, but you can go back and do Wilson theorem if you want, and you can prove that it's a prime number. And, ooh, not that yet. And this is one of many. And this leads us on to Green-Tao Theorem, which I've got a story about Ben Green. But this is one of many equations. I put one here because I find it very amusing. This is something that came out of a very famous theorem that is kind of prime number theory. And probably most mathematicians would have heard of Terence Tao. And Terence Tao and Ben Green. Ben Green is a combinatorist at the University of Oxford. And Terence Tao, I think he does number theory, he does a bit of everything. And they came along and they said, right, this primes thing, surely it can't be that hard. And they spent a good couple of years looking at primes, thinking about them, and they came up with a theorem. And then somebody else came along, it's not actually named to come up with this, but they said, okay, I'm going to use the Terence Tao and Ben Green theorem, and I'm going to produce this equation. This equation in front of you, which is 224, 584, 605, 939, 537, 911, plus 181, 356, 965, 979, 489, 30n. It produces primes wait for it, between 1 and 27. Okay, it's not as good as our quadratic, but it's only a binomial function. So it's only got two things in it. It's got the constant and it's got the end term. So for something that's simple, it's a very big inverted commas here because it's got funny coefficients. But for it to produce primes between 1 and 27, I think that's really amusing. I quite like that. I think that's really good. But let's talk a bit more about what this Tau-Green theorem is. Scary slide alerts! Oh, we're all right. We're going. Yeah, right, sorry. Yeah, I'm aware it's affecting my audio quality. My computer is complaining. So, you've got two very lovely people in front of you. Terence Tao, which is the person, I don't know if you can see my cursor, but he's the upper person. And we've got Ben Green, the lower person. I've actually met Ben Green. I didn't know I did. I was at IMO last year doing a few things. And I was walking around and I sat down at a table. I had a drink and Ben Green came over. He said, "Hello, you seem to be an IMO person." I was, yes, I am. And he just started talking to me about maths. And I had no idea who he was. And he was this person I'd read about in many books. And I was like, I didn't realize until I came home. I was like, okay, this is Ben Green. That's interesting. But what he did with Terence Tao was something that you may, at the end of this, say, talk is over. We're done. But there's a few caveats. It also may blow your brains out, depending on how mathematical you are. But I think this is honestly interesting. We can find a function with a and b being some numbers, any numbers you want. We're probably going to be big and large, where a and b are just numbers, and a plus bn produces a prime for all n. Confusing words, very confusing words. But what I'm saying here is what you did for that quadratic earlier, when I told you to square the numbers, subtract 1, add 41. They said that in a different world, well, in this world, on a different time, I could tell you, okay, here's a number. I want you to times your number, and your number can be any number you want. 50, 30, 47, 37, 12, 123, whatever you wanted. And you can take that number and you can times it by some other number and add another number. These numbers were large and you probably couldn't do them in your head, but still they exist. And everybody, no matter what number they chose, will have a prime on their piece of paper. Technically, it says we can find a function which produces k prime outputs, where k is any number of our choosing. So instead of for all n, we can find a function where we have inputs from 1 to 50 or 1 to 75. But I've just chosen n to be sufficiently large or large enough such that everybody in the audience, whatever number they pick, well, it will be a prime on your piece of paper. But it's an existence theorem. And no, at the end, I'm not proving this one. We will be here all evening, all the way to tomorrow morning. So no, this is not one of the things you've asked me to prove, I'm not proving. But yeah, you may say, okay, James, we've got a law and we've got a pattern to the primes. Kind of. You say, yay, we're done. Brilliant. I can stop listening to this boy talking about primes. Yay. No, not so fast, bucko. We have a theorem saying it exists. Not that we can grab this from formula and find all of the primes. It exists somewhere, but we don't have a pattern in our hands. It's like me saying, okay, I have a chocolate bar in my hand, but the chocolate bar's in Aldi. Other stores are available, but Aldi's the closest to me. I can't just say that, unfortunately. So we have to keep searching. We know it must exist somewhere, however infallibly insane this is. I'm aware what I've just said to you makes me sound like a complete and utter madman. There is a formula right there for all the primes, and we can put some numbers in and we get primes. Amazing, brilliant, but not so fast. So how do we know how big the primes are? GIMP, the Great Internet Mersenne Prime Search, okay? So people all around the world use their computers to check possible Mersenne primes. This is something called, I think it's group computing, where people sit there and they download this software and it just uses their CPU and GPU to just find primes. The same, I think, folding at home is the same, and many cryptocurrencies use the same kind of thing. But there are also a load of viruses that do the same thing. But this isn't a virus. This is you wanting to download it onto your laptop to make, or computer to make primes, find primes. And a Mersenne prime is a number of the form 2 to the n minus 1, where n is just a whole number. Because if we have fractional numbers, I'm not going to go into that tonight, it gets messy. So, a little question for you before the break. The answer will be after the break, so have a think. How many digits does the largest prime, which is incidentally is Mersenne, have? Or what is this prime? So think about it over the break, and I shall see you in 15 or 5, or whatever the break is, minutes. End of part 1.
Call it 5.
Right, let's go. Yep. Hopefully it's doing, are you seeing things? No, it's not doing that, okay. That's fine. Let's try again.
Also, your microphone's not quite where it was before, so you're a bit quieter.
Oh, sorry, my fault. I'm not sure what it's not doing.
No, you're sharing your own screen, I think. Are you? No.
I'm trying to. Right, hey, hello. Part 2. Let's go. Right. Oh, wrong one, and that one. Right. Who in the chat I asked for talking about? Let me go back to this. Go back to slides. Before the break, I asked about how many digits do you think that the largest prime, which incidentally is Mersenne, has? Anybody got any answers? Chuck them in the chat. See how close you were. Oops. And I can't see the chat. I'll come back to this later then, because I can't see the chat. Let's see how close you actually were. So, what is the largest Mersenne prime, which is incidentally the largest prime? We have a graph here, which I find quite amusing. That the largest prime, which Mersenne prime, was 2 to the 82,589,933 negative 1. Because it was 2 to the n negative 1. I never said how large n had to be. This has 24,862 and 48 digits. Now that's a lot of digits. This is Mersenne prime 51. That's not many Mersenne primes, given how big this number is. It kind of gives us this imagination of how far apart primes actually are. Because if we look at this graph here, we can tell that it's logarithmic. So these, it looks like a linear regression, probably is the right word. I'm not a statistician, but actually these points are two to the whatever this distance is apart. So they are a lot further apart. So the distance between probably that one and that one is, I don't know if you can see this, but double that one and that one. Even better, that one and that one, that one, that one. But they're very far apart, and primes get ever so less dense the larger they get. Because when we're talking below 10, we saw that you have 2, 3, 5, 7, it goes 11. But given that Mersenne primes have to get to 25 million digits in length in order to be above 50, the number numerical of there has to be more than 25 million digits in order for there to be more than 50 Mersenne primes. That really says something. So also this is 500,000 digits larger or longer than Mersenne prime 50. This isn't in size. This is the amount of digits. So thinking from 10 to 100 to 1,000 to 10,000 to 100,000 to 1,000,000, how big those numbers get then. Think about adding 500,000 digits on the end. Think about how big that number would be. It would be massive. So these primes, they're not small numbers. Well, they're not anymore. So when I was talking about the sieves earlier, we really need more effective sieves. So, patterns in application. Anybody from my degree course will be very happy now because they all love applications in maths, and I don't. I'm a pure mathematician at heart. So we're going to look at something called a cicada, and polygons and partitions, so geometric applications of primes, and cryptography. Cryptography, we're going to melt your brains a bit, but melting brains is all part of the process. So, look at this ugly bugly. This is our friendly cicada. There we are. Isn't that unpleasant? They're unpleasant little creatures that make the worst noise known to man. But these noisy blighters love primes. So, if you live in, I think, Australia, New Zealand, the US, probably other places they've moved to, you will know that sound very well. Well, if you've lived in the place more than 17 years statistically, or you've been unlucky enough and you've lived there less than 17 or 13 years. Because they love primes. I don't think we quite know why. Well, we know predators, but that was kind of, when I did my research, very wishy-washy. I didn't like that reasoning. But it may just be a coincidence, but they come out of hibernation every 17 or 13 years. And we know that they are primes. And I find that amazing. These little creatures make the most annoying noise, but they're also the most mathematically interesting. Well, depending who you are, so I think they're very mathematically interesting. Let's listen to that noise once more for the road. Yeah. It's not nice. It's very unpleasant. Also, another fun fact, they can't jump. They're unable to jump. They can fly, but they can't jump. So, polygons and partitions. We're going to spend quite a long time in here, but I've got a nice little diagram here. What I'm drawing, or what it is drawing, is a pentagon through some method, probably Pythagorean method or something. I don't know. I don't study classical geometry, but you can draw shapes using just a pencil and a compass. Amazing, brilliant, lovely, love it. So, compass and straight edge, pencil, brilliant. But when can we construct a polygon or a regular convex polygon, or however you want to put it? How can you construct them with a pencil, straight edge, compass, whatever you want? The answer lies in Fermat primes. A Fermat prime is a number that is of the form 2 to the 2k plus or minus 1, dependent. And it may be a surprise to you that you can only construct a polygon using a compass and a straight edge if the odd divisors of the number of sides that the polygon has is a Fermat prime. Again, I'm talking maths and it's confusing. Let's go for an example. So the Fermat prime, as I've said, is of form 2 to the 2k plus 1. We've got a bit of a stack here, which is interesting. We do like a stack. There we are. We do like a stack. So let's take 5 is a Fermat prime because we can do 2 to the, let me go over to my visualizer because this is slightly harder to think about. So if we do 2 to the 2 to the 1, that is, well, we go from top to bottom. So that's 2 to 2, and then that's 4. Probably plus 1 is 4 plus 1, which is 5, which we can do in our head quite nicely. So what if it's 0? We can go 1 plus 2 to the 2 to the 0. Again, we do the top one first, which is 1 plus 2 to the 0, which is 2. And how did I create 3? I don't think I did create 3. I may have a just brief over 3 because I created it somehow and I can't work out how I created it. But we can create, if we take a polygon, oh, we've gone too far. We take a polygon like a 5-sided polygon. We can do this construction that you've been watching on the left-hand side, not paying attention to the maths. We all know you're doing it, so don't worry about it. You can only do that because 5 is 5 times 1, it's a prime, and we know that Fermat, well, 5 is a Fermat prime, so we can construct it using ruler and pencil and straight edge. So if we move forward a bit more, we can talk about other polygons that we can't construct with just a ruler and or straight edge and pencil and compass. If we talk about other polygons that require an angle trisector, like a triangle, I believe, we can, well, a triangle, you can construct it, but the angles are 60 degrees. There, you've got 60 degrees. And we know that if the angle is 60 degrees, it's a third of 180, so you have to do an angle trisector in order to kind of get that 60 degrees. So when can you construct a polygon that has an angle trisector and a straight, that can be constructed with a straight edge and a pencil and a compass? Easy. You just use something called pierpoint primes, which is another class of primes. I should also mention that there are ludicrously many primes. There are many different classes for as many people that have studied them, which is a lot of people, given that I'm doing a talk on it. Oh, we love a bit of gym. So we can do this if the number of edges that shape has is divisible by 2, 3, or a number of pierpoint primes only. So I think we've got an example down here. A pierpoint prime is scary as well. It's scary. Everything's scary. So it's of the form 2 to the n times 3 to the n plus 1. And I've lost my notes on how to get to my visualizer, so we'll go back here. We'll work it out. Shift, notes, control. So we've got to, come on, behave. Oh, it's not actually, it decided to not work. There we are. Right, come on. Are we going to, are you going to work? Are we going to see my visualizer? Yeah, the visualizer's back. So if we take we just said that Pierpoint primes, PVP, is the same as 2 to the n, 3 to the n, plus 1. Okay, so we can take a Pierpoint prime of 2 to the 1, 3 to the 1, plus 1, which that is, well, sorry, probably put the time sign, which is 6 plus 1, which is 7. Okay, so 7 is a Pierpoint prime. We can do, again, 2 squared times 3 to the 1 plus 1. That is 4 times 3, which is 12, plus 1, which is 13. 13, yeah. And we can carry on going, and I think I've made another numerical error in my slides, but it doesn't matter. I can just correct it here. So 7 is a Pierpoint prime, and if a number is divisible by 2, 3, or a Pierpoint prime only, then we can construct it using a straight edge, a pencil, a compass, and an angle trisector. And there isn't, I'm okay. So we construct a 42-sided shape, where 42, because 42 is 7 times 3 times 2. Okay, so we've got a Pierpoint prime, which is 7. We have a 3 and a 2, which we said was by 2, 3, or Pierpoint prime. I'm not going to construct a 42-sided shape for you. I know how upset you are, but we're not going to do that tonight. As much as I wanted to, I decided your time was too precious. So, last lot about polygons and partitions. We can split a convex polygon, or a shape, if we're going to be less mathematical. We can split a shape, so like a square or a triangle, into smaller portions. But the amount of sides need to be a power of prime. So like 2 squared, because 2 is a prime, but not 6 squared, because 6 is not a prime. So we could have 3 squared, we could have 2 cubed, or we could have 5 to the 7 if you wanted to. I'm not going to split anything like that, but it gets cooler. If you have a square with, you should have a square in front of you, or a shape with a square, power of the prime number of edges, then these portions are able to be equal. So you can split it like a pizza, right, if you're doing it fairly, really. If you take a pizza, you can cut it into like equal slices. You can do the same with any polygon, as long as the number of edges it has is a power of a prime. So let's take an example of a square. Back to the visualizer. Which, I'm so sorry. I'm so sorry. I'm so sorry, but it doesn't matter. I've explained it fully. We can just take a square. I didn't see that. Doesn't matter. We can take a square. Here's a square. It's got 4 sides. 4 is 2 squared. It's a power of the prime. So we can split it down there, and through some quick geometric stuff, we can go like that. Okay, that's a on 2. Then that will be again a on 2. So that's just half a on 2 squared times 2, which is a squared on 4. And 4 of them make a squared, which is the area of the square. So we've been able to split it in a way that all the areas are equal. Jolly good, fun, done, yay. So, let's go back to slides this time. That'd be good. So, polygons and partitions, brilliant. You can do stuff with primes and geometry, and it's fun. Shapes are nice, I like shapes. I'm an aspiring differential geometer, which is kind of like stuff to do with shapes and space and It's like, it's fun. I enjoy it. So geometry is nice. Right. I think a couple of you will be excited at this point, and I'm sorry, it's going to be underwhelming. But this is kind of where primes are used in everyday life. I can promise you that all of you use a prime on a weekly basis. I can probably say that all of you have a bank card of some kind. And if you could put your number on the front, 3 digits in the back, and the name of your mother's maiden name in chat, that would be lovely. But that's not the point. We can have a prime, well, the use of prime come up in everyday life. And you may not expect this from something so pure and mathematically hardy. We can look at cryptography, which is the science of making things secure. And when you buy something online, what keeps your details safe is the fact that primes are extremely hard to factorize and have very little pattern. So this is basically going against the whole talk, but it's very useful. One of the most well-known uses is called a Diffie-Hellman exchange. Let's explore how primes are used in this using 2 characters, Alice and Bob. So, the Diffie-Hellman is used to exchange secrets between people without explicitly telling the other person your secret. So it's a bit like a guessing game, but without guessing and more maths. So it's not really a game to most people, but it's useful. So let's play the game. Scary slide alert! From Diffie-Hellman. Alice and Bob publicly agree to use a number, which I call a modulus, 23, and another number, 5, which is something called a primitive root, but we won't worry. They're talking about 2 numbers. We have 2 numbers, 23 and 5. And we're going to do some funny calculations with them. And I'm going to explain them, so don't worry, don't be scared. Don't be scared with the numbers. So Alice chooses a secret number, a whole number, which means an integer, 4, let's say, and then sends Bob a number, which is 5 to the 4 mod 23, which we saw earlier, means 5 to the 4, the remainder of 5 to the 4, divided by 23, which is 4. So we've got Alice sitting here with her number 23, which both of them know. They both know the number 23, and they both know the number 5. So we take a number, our number's 5, and we take 5 to the 4, divided by 23, and that's 4. Well, the remainder is 4, sorry. Then Bob chooses a number, any number. And the aim of this game is then to understand what each other's number is. And then Bob sends Alice another number. But this number is 5 to the power of 3, divided by 23, then take the remainder of that, which is 10. So they've both taken their secret number and taken the public numbers and they've taken the base, which is 5, raised it to their secret number, divided it by the modulus, which is 23, and find the remainder. So they've both got secret numbers. And they've both sent it to each other. So Alice now knows, well, Alice knows 10, Bob knows 4. And now Alice computes something else. What this does is it's a sort of inverse kind of wavy-handy maths. So Alice takes the number that Bob gave her, which is 10, and raised it to the power of her secret number, which is 4. And then she divides it by 23, which is the publicly known modulus. And then they take the remainder of that, and she gets a new number, which is 18. Bob does the same. he takes the number that Alice gave her, 4, raises it to the power of his secret number, divides by 23 and takes the remainder. It's also 18. Then they share the number that they both created, which is 18, and they know that they've got the same, or they've got the proper information. From this, they can do some other calculations and work out what the other person had, blah, blah, blah. But you can share information, or make sure you can know that the other person has got correct information even without sharing it. This is what Diffie-Hellman does. Same thing happens when you buy something online. This happens between your phone or your computer when you buy something online, and Amazon or eBay or Waterstones or whatever you buy stuff from. This is what happens with the computers. They do it in a click of a second, but that's computers. This is what they do. And it's all to do with primes. It's because primes are extremely hard to find the factorization of, but they have some funny properties when you take modular of them. So when you divide things by them and take the remainder, they have lovely properties. Basically, it boils down to saying that the numbers A times B is equal to B times A. That's what it boils down to. So I'm checking I'm showing the right thing. Oh, I'm not showing the right thing. That's fine. It's that one. Yeah. It's A times B times A. That's what it's saying. That's what the whole thing boils down to mathematically, with a few caveats as per usual. Oh, you can't see what I'm doing. That's brilliant. I'm glad to see that. Right, let me move this out of the way. Move me out of the way. Behave. No, we're not going to move me out of the way because there. Move down here. There we are. Now you can see. Sorry. Didn't know that. So you can see that I go through this again. They publicly share a key, which modulus of 23 and a base of 5. Then they share a secret integer, and that's the bit you couldn't see. So basically Alice chooses the number 4 and then calculates this 5 to the 4 divided by 3, take the remainder, and that's 4. Then you can do some funny maths. You follow the same procedure I said before, and they both get 18. I'm happy to talk about this a bit more at the end because this is a bit confusing. So next, I may have to move myself. Now this is the last section. The second section of the talk is a bit shorter than the first. I'm sorry about that, but these are just some interesting things that I thought I would mention. These were things that if I mentioned in greater detail, I would blow your brains out as they blow my brains out, and they're a bit confusing. So what we're going to talk about is the Riemann-Zeta function, which some of you may be already quite acquainted with. It may be your friend. And we're going to talk about the search for the truth, which is basically a fancy name for me telling you that there are no patterns. At least we don't think so. We don't know. It's my wrapping up bit. Also, I found an interesting little thing in my research, and I thought it'd be a good thing to talk to you about it. It's nothing to do with primes. I just thought it was interesting. So let's go. Right. Scary slide alert! This is more mathematical gubbins, and again, if you next slide is very, very scary. But don't worry, we'll go through it together and we'll take our time. So, don't scream, just look, it's okay, don't worry, it's only a bit of notation. So, the Riemann-Zeta function. It's probably one of the most famous mathematical problems in the world. It's part of the Millennium Problems, which were, I believe, 10 problems set in the year 2000 to be solved. And there is a £1 million prize for any mathematician that can solve it. The Riemann-Zeta function, it's basically the problem is stated along the lines of, okay, here's a function, prove that all the zeros, or when zeta of s, that's what this funny little squiggle is, zeta, prove that zeta of S is 0 at all of the positive, I think positive integers, and then negative integers, and then find some stuff out about the negative half. There's some funny things going on there. So basically, prove some things about the Riemann zeta. It goes into more detail, but it's confusing. So the Riemann zeta is a symbol function. It takes in a number, which is S, any number, real or complex. Shh, I used a funny word, complex. A complex number is basically square root of -1, blah, 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 hand wave mass. It's a thing. And it does funny things. But we're not interested in that. We're interested about the fact that it can be written, this sum, this means this funny sigma thing. This means you're summing from n equals 1 to infinity. So it's saying this unfolded is, me go into my visualizer, control, right. There, we've got summation from infinity from n equals 1 of 1 over n to the s, which is 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, plus blah, 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 blah. So it unfolds it basically. Well, this funny thing here, which is a sigma summation notation, basically means plug in 1, then plug in 2, then plug in 3, then plug in 4, then plug in 5, then plug in 6, then plug in 7, then plug in 8, then plug in 9, all the way up to infinity. So basically don't stop. And we can let if we let s equal 1, so we get something of 1 to 1 to the 1 plus half, plus a third, plus a quarter, plus a fifth, plus that just doesn't exist. It blows off to infinity. It doesn't kind of stop. So we say that's to infinity. And if we let s equal 2, I believe it's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. If I remember correctly, this is pi squared on 6. I think so. I think it's pi squared on 6, which is pi. It's 3.141592 blah. I don't know anymore. But it's the circle constant, and we're talking about numbers. And oh, sorry, I forgot the blah, blah, blah. But it's pi in a summation that's got nothing to do with numbers. Isn't that amazing? I think that's amazing. But this is not primes. This is what this means, but we're not talking about primes anymore. We've gone slightly off the rails, which usually happens, but we can write this in a different way. We can write this as the product. Product, that's what pi means. Pi means product. Oh, there we are, make sure we're here. Prime is product, okay? So we're gonna times, let p be prime. And again, we're taking an s. So we're going to go for product where p is prime of 1 over 1 minus p to the negative s, which is 1 over 1 negative p to the negative 1. Then, 1 to the s, 2, because 1's not a prime. 1 negative 2 to the negative s times 1 over 1 to the 3 to the negative s, blah, 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 blah. And it comes out the same notation. It comes same number. So if you let s be 2, that's the same as this. That's also pi. So if s is 2, that is equal to pi squared on 6, right? We don't need to worry why. I'm just getting excited. So basically, it's about finding patterns in the primes, hand-waving mathematics, and x is negative 1/12, which is a joke because there was a massive thing a couple of years ago about the fact that this sum here, if we do some actual proper sound mathematics, hand-wavy, inverted commas, we say that it's equal to negative 1/12. You can do some high-level mathematics and say that this infinity is negative 1/12. It's not actually that, but I just thought that was interesting. Where it comes into primes is when we do something called the extended Riemann zeta, which is kind of complicated, hand-wavy. And you've got some functions and you've got some arithmetic progressions. Functions being like our quadratic earlier, and our arithmetic progressions, meaning you can take a sequence. It's just a sequence. So 1, 3, 5, 7, 9, which is just the odds. That's an arithmetic progression because it progresses by a single one each time. It progresses by 2. So it's just a sequence where you add 2 each time. Same happens for primes. If we can prove that the extended Riemann hypothesis, or extended Riemann zeta, whatever you want to call it, we can take primes and we can find a arithmetic progression. Okay, but this difference here won't be just a number. It'll be some sort of function. But if we can solve the extended Riemann zeta function or extended Riemann hypothesis, we can find a pattern in the primes. This is what the talk's been leading up to. So, how do we find a pattern in the primes? Well, we solve the extended Riemann hypothesis. How do we solve the extended Riemann hypothesis? I don't know. If I knew, I wouldn't be sitting here in front of you talking about extended Riemann zeta function. I'd be the next Ramanujan. Unfortunately, I'm not. I'm not the next Euler. I'm just sitting here telling you about this. I don't know how to solve this. Some of the best mathematicians are working on it. We don't know if there's patterns in the primes. We don't know if this is true, because every mathematical statement can be proved true or false. So, unfortunately, as close as it is, we can get so close with some very advanced maths. We're not quite there. And that is basically it, bar this very interesting thing. When we were talking about primes earlier, we were talking about infinitude of primes. There's also another interesting problem relating to a function, which many of you may know is a plus a to the m plus b to the m is c to the m. That is described as Fermat's last theorem. If we let n equals 2, this is old faithful Pythagoras, which has solutions. N is greater than or equal to 3, has no solutions. So, a cubed plus b cubed equals c cubed. Is it greater or equal? I think it's greater than equal. Yes, it is greater than equal. It doesn't have a solution. This is another interesting thing that was written by Fermat, our friend. We talked about Fermat earlier with Fermat primes. Fermat said that there are no integer solutions for n greater than 3 of this equation here. But he wrote it in the margin of a book. And that book was too small to hold this proof. And so we never got a proof. And we never got a proof. And we tried to solve it. And then an Oxford mathematician by the name of Andrew Wiles locked himself away in his attic for, I think it was 3 years, if I remember correctly. And he solved it. He solved it in 2000 and something, if I'm correct. I can't remember exactly when, my memory's going. But he solved it. But I've got a better way to solve it. He did it with all this complex mathematics. Well, I've got a better way to solve this. But I've got a better way to solve the infinitude of prime problems. This isn't my paper, I've just found it. But if we take the solution to this, we can do some fancy mathematics, which I'm not going to show you, but I'm going to tell you that the solution, there being solutions to this equation, implies that there is an infinitude of primes. And that is me done. Ah, 1998. That's when prime. That's when it was solved.
Thank you, James. That's quite a tour de force for us all there.
I'm glad I broke your brain.
And well, there's a whole host of questions here. I don't know the right way to tackle it. Normally we've got a string of ones, but there's so much going on as we go through. It's hard to pick all of it out, I have to say.
Shall we start with a round of applause for James?
I think we certainly should.
I think we do, yes.
Thank you.
Thank you, James.
Thanks, James.
Thank you, Chris. Oh, and just in time, I finished my gym.
Oh, yeah. As someone who definitely didn't even do A-level maths, that was bringing back some scary memories, James, I'm not going to lie.
I'm sorry. I tried to make it as least scary as I want. I at least warned you when it got scary.
And to be fair, they were rather cute penguins that sort of softened the blow a little bit. Speaking as a biologist, that did soften the blow slightly.
I did try to distract you with the penguins.
Okay, I'm flipping through these questions now.
Oh no, I'm going to have to explain Green-Tao Theorem. Oh no, I tried to quickly Google this during the break.
You did the A a bit, that one.
Right. Phase.
James, are you able to see the chat?
Oh yes, sorry. I'm getting. Yeah, let me have a quick look. Right. So
this might be me being a bit dense, James. I'm not going to lie, but just going back to your one about how many digits were in your. Is it Mersenne prime?
Mersenne, yes.
Mersenne prime. How do they know that there's going to be that many digits if, like you said at the beginning, if there's always going to be another, if there's always going to be another one, if they're a bit like rabbits, how do you get to this? This is how many digits we've got.
Let's go back. Can we show? No, I tell you what I'm going to do. If I can go to that one. There we are. So, back to this slide. We know that there are that many digits in the prime. Well, the question, sorry, I'm getting distracted again and excited. The question was, we don't know. The problem is, they're saying that we have found a prime with that many digits. Probably it was my fault for the question being so it's a very convoluted question, because yes, there's always one bigger. But the biggest we have found is probably what I should have said in the question. The biggest we have found is the one I've got. It's the 25 million one. That's the biggest we have found. Sorry, that was probably my fault with the wording of the question.
No, then we've got some bits about cicadas and how noisy they are.
Oh, they're awful. I hate them. Hate them.
I think, yeah, well, we've got one from Tariq here. Look, probably a bit philosophical. Is it perhaps that some things just can't be proved?
Yes. Gödel incompleteness theorem says that things can't be proved in a very quick sense. Some things can't be proved, some things can be proved. There's another problem called P versus MP, which is all about kind of whether things are computable and solvable. So yes, some things can't be proved.
Can anyone hear me?
Yes, we can hear you.
Yeah. Oh, fantastic. Earlier on, you said something about things of the form a plus bn always being prime, and I didn't quite understand that. Are you able to just sort of say it again briefly, or point us to something I can read?
Yeah, I'm not hugely read up on this.
Okay. I
Because
can Google it. What
it's-
should I Google?
it's the Green-Tao Theorem.
Okay.
That's
all right.
what you should. I'll link the Wikipedia article because I love Wikipedia for this sort of thing. Because honestly, I could probably direct you to a book or a paper probably. But it's very dense stuff. If I'm perfectly honest, this sort of thing is very dense, and it hurts my head quite a bit. And I don't understand this, so I don't want to tell you something incorrect that I don't understand. I just stated the theorem and say I'm not proving this because honestly, I'd get it wrong.